from the somewhat abstract symmetry of the previous section to the very practical two-stage random experiment. And the first example I'm going to use is a totally made-up example, and what it does is it gives me the pleasure of using the word widget. So you've got a factory and it produces widgets. Many of you will know that the word widget is a nonsense word, which means another nonsense word, thingamabob or doohickey. It's just a thing. And you can in your mind imagine it to be any thing that you want. So you've got a factory and it's got two machines, and machine A produces 80% of its output. And so if you pick one of the widgets at random, then the probability that it is produced by machine A is 0.8. The remainder are produced by machine B. So the probability that your randomly picked object is produced by machine B is 0.2. Okay, so that's the first stage. This object is produced by one or the other machine. And the second stage is you take a look at it. It's either a good widget or a bad widget. 1% of machine A's widgets are bad. So what does that mean? That means if you restrict your attention to the widgets produced by machine A, then out of those 1% are bad. So in the language of probability, the probability that a randomly picked widget is bad, given that it came from machine A, is 1%. And machine B messes up as well. In fact, worse, 2% of its widgets are bad. So the probability that a randomly picked widget is bad, given that it came from machine B, is 2%. And now we're going to look at that randomly picked object and try to answer some questions about chances. But there's a lot of chances and numbers floating around, and so it is a very good idea to arrange this schematically in a diagram. And the simplest diagram is one that I hope you will sketch routinely now, and that is called a tree diagram, and it looks like this. So there are two stages. First is the machine stage, and at the end there's the good-bad stage. Alright, so the machine's either A or B, and so your tree, this is the thing that looks like a sort of horizontal tree. Your tree splits like this. There's a branch that goes to machine A, there's a branch that goes to machine B. On the branch, I've written the corresponding probability. Okay, so now here are all the widgets made by machine A. Some of them are bad and some of them are okay. Here are all the widgets made by B. Some of them are bad and some of them are okay. And what we have written are the probabilities of ending up, in this case bad, given that the object was made by machine A. Equally, the probability that it is good, given that it's made by machine A. And what are we learning about these decimals? Well, if you start at what is called a node, if you start at any one of these points, and you look at all the branches that you end up at, these must add up to 100%. Right? So you start here, and you look at these two that you end up at, these two must add up to 100%, because this is all the output from machine A. Right. So this diagram encapsulates all of the text of the description up there. And now we're going to start computing some chances. We already have written down some chances. So here's your picture again. And what we've said already is that for a randomly picked widget, the probability that it is made by machine A is 0.8. The probability that it is bad, given that it was produced by machine A, is 0.01, that's 1%. So if I take a randomly produced widget and I ask you, alright, so this one, what is the chance that it was produced by machine A and it's bad? Then what have I asked? Then I've said, what is the chance that it lies here? That it's one of these. And so what are you going to do? You're going to say, well, first, it has to be produced by machine A. 80% are like that. And of those, 1% are bad. So my answer is going to be 1% of 80%. There's your multiplication rule. The chance that it was made by machine A and it's bad is the chance that it's made by machine A times the chance that it's bad given that it came from machine A. And there you have it, 0.008. So what you've seen is that if I ask you what is the chance that your widget is in this branch here, you multiply the probabilities along the branches. Alright, so now I've stuck my hand and I've pulled out a widget at random and I ask you what is the chance that that thing is bad? Well, where is it in my picture? Well, it's either here or here, which means it's either in one of this branch or this one. It's either bad and came from machine A, or it's bad and came from machine B. There is no third option. And we know how to compute each of these individual chances. We just multiply along the appropriate branch. So 0.8 times 0.01, that's the first branch. 0.2 times 0.02, and that's the second branch. Add up, and that's the chance that that object is bad. These are just proportions. We're just working with proportions. You're looking at the total proportion bad, and you're breaking it up according to which machine it came from. That's all. And so it is easy to use tree diagrams to calculate probabilities. And what this does is it sets us up to calculate a kind of conditional probability that we haven't computed before. There are conditional probabilities that we've just written down, which I call probabilities in chronological order. The thing is produced by the machine has a certain quality, and so given that you know what machine it is relatively straightforward based on the conditions of the problems to simply read off the conditional chance that the object is bad. But what if I do this? I pick a widget at random and I look at it, and lo and behold, it's bad. And now I want somebody to blame. So I ask, well, what is the chance that that bad thing came from machine A? So what have I asked? An item is picked at random. I want the chance that it came from machine A given that it is bad. In other words, I want to go backwards in time. I'll tell you the result of the second stage. You give me chances for the first one. Okay, so how do we do that? Well, schematically, what do we know? We know that it's either here or there. And that becomes my total space. It's not here and it's not here. It's not on the OK branches. So these two branches total are my space, and all probabilities are computed relative to that. So where do I want it to be? I want it to be from machine A. So what I want is the chance of this branch, the top one, relative to the total chance of the two branches that I know the thing is in. So the chance that it's from machine A, given that it's bad, is the chance of the top branch, that is A and bad, divided by the total chance that the thing is bad. And we did all the bits in just a few minutes ago, but I've redone the calculations. The chance of this top branch is 0.8 times 0.01, and the total chance of the two branches is these two items summed. And when you do that calculation, you get 2/3. And what I'd like to do is I would like to imagine the size, so I would like to examine the size of that answer. If I didn't tell you anything about this randomly picked widget and I asked you what is the chance that it came from machine A, you would say 80%, because 80% of those objects come from machine A. But now I'm telling you something. I picked it at random and it's bad. So now which machine do you think it comes from? Well, the vast majority are made by machine A, but machine B is a worse machine. It has a higher rate of producing bad items than machine A does. So given that the item is bad, your chance that it came from machine A drops from the chance that you originally had. It drops from the 80%. It becomes less than that. And that is because you're thinking it's bad, this gives a little more weight to machine B. And that's what this calculation does, is it allows you to update your probabilities according to the information that is at your disposal. This method is called Bayes' rule due to the Reverend Thomas Bayes, and it is used to find the conditional probability of an event at an earlier stage given the result at a later stage. Its probability is going backwards in time. And this method is used a lot in all of your spam detection software and so on uses it. It updates its probabilities as to what kind of messages are spam based on information about what it's seeing. And so this is a nice, easy calculation that people enjoy doing. I'd like to use it in one more context, which is a little less silly than widgets, and take a look at where we need to be careful. And so this is the situation where you're testing for a disease. And I'm imagining a rare disease, 1% of the population has it. And there's a test for this disease, and the test result is either plus or minus. So when the test says plus, the test thinks that the patient has the disease. And when the test says minus, the test thinks that the patient does not have the disease. But tests are not free of error. Tests mess up. And so here are the error rates. This is not a terrible test. It does get the answer wrong. There are two kinds of errors. The person has the disease, but the test says no. That's one kind of error. And that kind of error, so among people who have the disease, half of 1% test negative. So that's one kind of error. That's a false negative. And among people who don't have the disease, 0.8 of 1% test positive. So they get their result back, and it's positive, but they don't actually have the disease. And that is called a false positive. So there are two kinds of errors, and they are distinct. And most tests make both of them to some extent. And so the question that we're going to ask is the question that is of interest to most people, which is they've taken the test and they've tested positive. Do they have the disease? So specifically, what is the question that is being asked? You pick a person at random and test that person. Given that the test result is positive, what is the chance that the person actually has the disease? It's not 100% because the test doesn't always get it right. So what do we do? Well, this is a two-stage experiment. The person either has the disease or does not. And then they get tested, and the test either gives a plus or a minus. So let's make a diagram. And so here are all the numbers in the problem in a little schematic. So there's disease or not disease. 1%, 99%. Given that somebody has the disease, the chance that they test negative, that is an error, is 0.5 of 1%. That's 0.005. And therefore, given that they have the disease, the chance that they test positive is very high, 0.995. Equally, if they don't have the disease, the chance that they test plus, and here's your false positive, is 0.8 of a percent, and correspondingly the chance that they test negative, given that they don't have the disease, is 0.992. And so what was the question? The question was, well, we've picked this person at random, they've been tested, and they're here. They're in one of the plus branches. So what is the chance that they actually have the disease? What is the chance that they're in the top branch, given that they're in one of these two branches? Well, you know how to do that. The chance that they're in the top branch, given that they're in one of the two plus branches, is, well, the denominator is the total chance of the plus branches. So 0.01 times 0.995, that's the chance of the top one, and then 0.99 times 0.008, that's the chance of the bottom one. And you want the chance of the top one relative to all that. And once you've done all the calculation, you have 0.56. And that is simply an application of Bayes' rule to this situation. So as a calculation, it's easy enough to do. As an answer to understand, it raises certain questions. This test is okay. I mean, its error rates are relatively small. I mean, they're there. The test could be better, but it's not dreadful. And yet, look what has happened. The person has tested plus, and we're saying the chance that they have a disease is around a half? This is like tossing a coin. What good was that test? And so this is where you have to understand what were the assumptions on which this problem was done. And the critical assumption was that the person was picked at random and tested. And for a person who is picked at random and tested, indeed, if they test positive, the chance that they have the disease is around a half. And why is that? Well, the test is pretty good. The error rates are small. But correspondingly, also very few people have the disease. So the people who have the disease and test plus, that proportion is comparable to the people who don't have the disease and test plus. And that is why this proportion is close to a half. So then you sit back and wonder, well, then is the test useless? Right? Because you go in, you get the test, it's plus, and now you have to toss a coin to figure out whether you have the disease or not? Not quite. What was the assumption? The person was picked at random and given the test. The person picked at random from the population and tested. Is that the way people normally get tested? I don't think so. Patients who go to get tested go because they think there is some reason for them to get tested for that particular disease. And that immediately makes them not randomly picked from the population. And so this 1% was the 1% of the people who had the disease, and for a randomly picked person, it is fine to put a 0.01 here for the chance that that person has the disease. But for a person who walks into a doctor's office wanting to get tested, this number first becomes subjective and higher. And so if you raise this number and correspondingly decrease this one, your overall chance will go up here. It will be a subjective probability. It will include this ingredient of what you think is the patient's subjective probability of having the disease. The point I'm trying to make here is that this answer, which uses population proportions, is correct only if the patient is being picked at random from the population. Any other kind of patient, it does not apply. And so the moral of the story, as has been all along, your assumptions matter. Be careful about your assumptions, and when you're doing probability calculations, before leaping into a calculation, look at the randomization.